Hi, everyone. My name is Dale McDiarmid, and I'm a member of the product team here at ClickHouse. In recent months, we've seen large language models, specifically ChatGPT, obtaining a lot of attention and the opportunities and possible risks this will bring to businesses. Tangential to this, we've seen discussions as to the technologies organizations will need to deploy to exploit these emerging capabilities. Today, I'm going to try and answer a related question, specifically whether you need a new type of database in the modern data stack to deliver these capabilities. Hopefully, by the end of this, you'll feel well informed in your decision making if this question arises. So before I answer this question, I'd like just to spend a few minutes introducing ClickHouse as it does relate to the wider topic. So what is ClickHouse? Well, ClickHouse is an open source, column-oriented, distributed OLAP database. Now that's quite a mouthful, so let's break it apart and explain why each of these is important. So we're open source, which means anyone can download, they can view our code, and they can use our product for free. You can also use our cloud offering if they want, and they don't want to host it themselves. But it's also Apache 2 licensed, and it's been around since 2009. So it's a mature, heavily battle-tested database. We're column-orientated. This just means we store the data on disk by column instead of by row, like a database like Postgres. And this allows us to optimize for massive analytical operations. We're distributed, so we scale horizontally and vertically, and we're an OLAP database, which is an online analytical processing, and it means we deliver unparalleled performance for aggregations and real-time analytics use cases. We achieve this by optimizing for scale and aggregations versus transactional databases like Postgres, which optimize for things like individual row updates and retrieving individual rows. So who uses us? Well, we're trusted by giants. I won't go into many of these, but there's some great examples here. Spotify uses ClickHouse to power Spotify for artists, giving real-time insights into listener behavior around the world to the music industry. Deutsche Bank stores market data, I think, all the way back to 1999 even, in ClickHouse, allowing analysts and traders to build market insights and implement best-in-class trading algorithms. And Uber recently moved their observability stack, specifically their logs, to ClickHouse before powering real-time log analytics and search. Okay, so let's move on to the question at hand. Why might we want a new database to deliver these new ML capabilities? Well, machine learning models have caused a new data class to arise in much larger volumes than we saw before. So this class, known as vectors, has existed historically, but not in the volumes that we find now. So a vector is basically just a list of numbers that encapsulates the meaning behind a piece of data. So it could represent, for example, the context and meaning behind an image, a video, or just a piece of text. And for now, let's just think of it like that. So it's just this list of numbers that represents meaning for a piece of data. And many applications require the ability to search these vectors, and this is a capability known as vector search. So what is search in this instance? Well, it just basically means taking the vector for a piece of data, like an image, and finding similar vectors for other pieces of data, and thus finding similar pieces of data or similar images in that case. Okay, so if we have this vector search capability, what can we actually build? Well, this isn't an exhaustive list, it's just some examples. And there's a few here that stand out to me. So historically, search or text search by companies like Google, and maybe you're familiar with Elasticsearch, really just focused on text. It's very much a lexicographical search with maybe some ranking functions like learn to rank mixed in, but it was very much focused on text. Now we can, with this new capability to search vectors, we can search other mediums like images and videos. So if you can represent an image as a vector and you can represent all of the images, for example, on the internet as a vector, you could take that image and you could find similar images to that. Broadly, that's how maybe Google image search works. We can also answer questions. So text search historically had no meaning. It was lexicographical search. Maybe you would use an inverted index, you would search, and maybe you had some ranking functions there to reorder those results, but there was no real meaning behind the results. So you would suffer from problems like punctuation differences between the text in the documents and the text the user was searching for. So if those were different, you wouldn't get any results. We can also use it for interesting problems like fraud detection. So if you can represent user behavior as a vector, you can search for for example, bad behaviors, or you could search for behaviors. You take a vector and say, is this one not normal? And find the ones and say it's not very close or it doesn't match normal behaviors, and thus it's a suspicious behavior. One of the more interesting applications that there's been a lot of blog posts online about recently is this notion of providing context. So I've taken this particular example from a blog post online, and this is where vector search is used to provide context to something like ChatGPT. So we've seen a number of these blogs, but generally vector search here aims to address the limitations of ChatGPT's training when applying to real-world problems needing more recent data. So ChatGPT is not only not domain specific, so it may not have access to some data that is relevant to the answer, but also it only goes up to 2019, I think December. So it's not real-world data. So suppose a user asks a United Airlines chatbot to change their seat. Well, the chatbot would pass the question, how do I change my seat, to maybe OpenAI, which will create a vector from this question that represents its meaning. If I've got all my answers stored somewhere as vectors, I can search and find a relevant or similar relevant answer text to the question, and then I can provide this to ChatGPT, which can provide a contextualized answer with information that it normally wouldn't have access to. And that allows us, as you can see, vector search here is fundamental to this capability. So we can see that we can search our list of vectors, and we can call them also vectors embeddings, I should say. Each of these just represent a piece of information. And by searching these, we can build these machine learning workflows and add capabilities to our applications. So this can be summarized as this kind of workflow. This is very, very high level, but we can take input data, images, text, video, provide it to a trained model, and we get vectors out. We store these somewhere, and then our applications and our machine learning models and workflows query these vectors and provide the results back to the application, providing that rich functionality that I've just described in the chatbot example. Okay, so this has led to this new class of databases arising. So there's a few here, but that's actually a lot. This is only a subset, but they all provide similar capabilities. So they provide an API to store vectors and an API to search them. And even in some cases, you can pass a piece of data versus just a vector, and it will automatically convert that into a vector using an inbuilt machine learning model and store it. And then you can provide, at search time, a similar piece of data. It'll convert it into a vector and find similar pieces of data, i.e. similar vector embeddings. But they all fundamentally are solving the same problem, which is the ability to search these vectors at scale. So historically, you would be limited to using a library, for example, which would be bound to the memory limitations of machine, and you couldn't scale this across multiple machines. And vectors allow us to scale, or these vector search databases allow us to scale this across multiple machines, thus solving that problem. And now this is particularly important as the number of vectors has increased. So if you have a few thousand vectors, a library, a single machine is probably fine, even maybe millions. But if you get to multiple millions and even billions, then you need some capability that can move beyond a single machine and not just be limited to what it can hold in memory. So before we move on and we discuss whether we really need these vector databases, let's just remind ourselves, we'll go into a little bit more detail what actually a vector embedding is. And I like to think of it as just more than just text. So that comes back to the notion of text search historically. We're now moving beyond text search. So a vector is basically just a list of numbers, whereby the number of values we describe as its dimensionality. So in this case, I've got a dimensionality of 10. I've got 10 values in my vector. And this can be very large. This can be 1,000 is not untypical for things like images. Sometimes 100 is pretty typical for text, for example, but it's generally much larger than this. But we're going to keep it small for brevity of the slides. So in this example, each position in my vector represents a kind of a sub-context. So we're trying to represent the concept of moonlight. And we have a value for each of our sub concepts. And in its aggregate, And when you combine these, these unique sequence of numbers represents that concept of moonlight. And this can be applied to images and videos. And it's the same principle. It's just a little bit simpler to understand in text. Okay, so now we know what a vector is. How are they produced? Well, they're produced, I alluded to this at the start, by these ML models. This particular model, I won't go into too much details. It's basically the CLIP model. So these models, I won't dwell on specifically how the CLIP model works. This is an open AI model that produces these vectors, and it can produce vectors for images and text. It does this as it was trained on around 400 images with their text captions. So these images were downloaded from the internet with their text captions. And the training process basically made sure that the vectors for the text and the images were as close as possible. So they were similar numbers. And it did this over all of the pairs of the images and captions. And now once trained, and you can download this model, we can provide text or images to this model, and it'll give us a vector back, and we can store these somewhere. So we can use it to solve a number of problems. In the image and video search here, we could take a set of videos, generate the vectors, store them, and then at query time, take a piece of text and find similar videos, or similar images. Not videos. And we can also do the inverse. So we could have text, we can generate a vector at search time for an image, and we can generate text for those or captions for those images. And this is useful in a problem known as zero-shot caption generation. Okay, so this is just an example of one of these models, and this is an open AI model, and it's relatively state-of-the-art. So now we know what a vector is, and we know how to generate a vector. Let's just talk a little bit about the importance of distance. So this is really what these vector databases are doing. So you can think of this easier to assume to think of this in 2 or 3 dimensions. In this case, we're thinking of some concepts in 3 dimensions, and we can visualize this quite easily and plot them as points. You might think the vectors which are close together on this plot are conceptually similar, and you'd be right. So our earlier search for changing seats is probably close to the vector how to move seats, for example, in our official help. We can compute this distance with a number of techniques. For 2 dimensions, it would intuitively just be Pythagorean's theorem. For larger dimensions, this actually scales fairly generically, this mathematics, and we can measure it with things like Euclidean distance. So importantly, the concepts, the notion of distance and the closeness is the same. We need the numbers to be close together in our vectors, and that means that those vectors are close and the underlying pieces of data are conceptually similar. Obviously, we can't think in 768 dimensions or 1,024 dimensions, which are common sizes, but the principles remain the same as in 2 or 3 dimensions. So now we know how to measure these vectors in terms of how do we know if they're close. We know what they are. We know how they're generated. How do we then search them? So searching them, there's a couple of techniques. We can either do it exactly. So we can say we've got our stored vectors for all our pieces of data. We can take our search vector, we can go through all of them, and we can measure the distance, then we can pick the closest ones. This scales linearly with CPU cores, and it can be quite efficient. I mean, if you've only got a few thousand or even millions, you can do this very, very quickly. You don't really need to even move to multiple machines, and you can also spread this computation across many machines. You can also do it approximately, and this is useful when the number of vectors gets much, much larger, or if you want to spend less compute time computing the closest ones, but it's approximate. Okay, so it's not it doesn't give you the exact result, but it might be good enough. And we basically sacrifice accuracy of the results for reduced latency. And this uses algorithms which are known as approximate nearest neighbor, or ANN. There's a number of examples here, HNSW, Annoy, least significant hashes, for example. And this can be useful, especially at large scale, or if we just don't want to assign the same amount of compute to the operation. So exact linear search might look like this. We have our stored vectors somewhere. We have our search vector. We run through them. We compute the distance for each one, and then we sort the distances, and we return the top n. Okay? And that scales pretty much with the number of cores that you've got. Approximate techniques, this is an example of approximate technique. This is the Annoy algorithm. You can just think that it slices all the vectors into a tree, breaks them into a tree, and it searches a tree. And you provide the vectors, and it navigates the tree, and it builds the vectors that it's been provided to store. And then that tree can be searched, basically. It's a little bit more complicated than that, but that's the basic principle. And this shows that kind of all those vectors being sliced into smaller and smaller pieces at the bottom of the tree, in a tree structure. Okay. So do we really need a specialist database for this is then the question. I say no, but with a well, maybe. So there may be a case that you do, but I think in most cases you probably don't. So my first thoughts on this are that why not trust decades of engineering? So existing databases support this vector storage and search just as another function in SQL. So Postgres supports this through PG Vector, which is a plugin, and ClickHouse supports it natively with just as an array of floating point numbers with distance functions built in. We support both linear and approximate techniques, so does Postgres. Neither are memory bound. Postgres provides transactional guarantees, and ClickHouse is proven to scale and is able to distribute computation very efficiently. Both are fully SQL compliant. ClickHouse has some additional SQL functions for analytical queries, but they both, if your users are familiar with SQL, they don't need to learn a new API or a new language. And they're highly parallelized and optimized query execution pipelines, which is perfect for this type of work. So often, if you just need to do vector searching, you can just use a DBMS. So when to use a DBMS? I would say if you need high performance and scalable linear matching with many cores, ClickHouse is specifically very good at this. If you've got metadata with your vectors as well, so it's often that they're not just vectors on their own, but they have metadata. For example, if I stored loads of images and the camera models as metadata with the vectors that these images were taken with, maybe I want to search for the closest vectors. I've got a picture and I want to say, this is a picture, for example, of a safari. And I want to say what cameras are taken, or what cameras are used for taking pictures of safaris. I can search for similar vectors and thus similar images to Safari and do something like a SQL group by and just aggregate on camera model. And that's very, very straightforward. So importantly, where I think vector databases are a little bit more distinct is that with DBMSs for vector search, they kind of assume that you have an existing pipeline for generating these vectors. So they're not vector databases. They don't have this built in as part of the database system. So you need to compute and generate these vectors through your model externally and just use the database for search, for storage, and search and retrieval. But they do support full SQL support. So if you need SQL support, it's a better option. And if you have a very large data set and do not wish to be memory bound, or a small data set by where linear matching is fine, again, DBMSs are more than sufficient. Or maybe you're using ClickHouse or Postgres already, and you just don't really need, you don't want to introduce another new database to manage in your infrastructure. As I said, you need to assume that you have this capability to generate these vectors already. So why might you want to think about looking at one of these dedicated vector databases? Well, there are cases whereby you would like to do some sort of hybrid search. So you want to do text search, things like Elasticsearch provide this, and then they provide vector scoring. So if you need these text searching capabilities and you want to add vectors as a scoring function on top in text search, that's a valid use case for something like Elasticsearch, Solr, or OpenSearch, all of which now support vector search. So again, if you maybe are thinking about not wanting to have all of these models to have to build them yourself, and you're looking for an out-of-the-box experience, technologies like Weaviate do have these kind of built-in, so you can just provide an image, Weaviate will generate a vector for you and store it, and when you search, you provide another image or a piece of text, and it generates the vector and searches for you. So those kind of inbuilt capabilities are a really powerful feature. Or maybe your data set is small and it fits into memory, in which case, maybe just use a library. Or you have a very, very high QPS rate, so you need thousands of queries per second. But even then, or tens of thousands of queries a second, that's not something that ClickHouse is designed for, but maybe Postgres still is. So again, maybe Postgres would be a valid choice in these cases, or maybe you want to explore a vector database. So in summary, vector search is essential in the building of modern applications with ML features. There's been a lot of noise around vector databases. And there are actually more vector databases at this point, probably, than traditional databases. And the speed of that emergence may also be some indicator as to the level of complexity that's required to build one. So often traditional databases are more than sufficient, and they offer vector search as a function. But there are valid use cases still for using vector databases, especially if you're looking for that out-of-the-box experience. So use ClickHouse for analytics and maybe also for vector search. Thanks for your time.